All right, go ahead.
Okay, I'm going to do this as a three-part show here, 3 different PowerPoints. The first one's going to be on the Dayton Microcomputer Association Computer Museum. And of course, we have a table back here at the back. And then the second one's going to be on my development of graphical programming system. If you think about things like LabVIEW, iconic programming, function block programming, Lego Mindstorms, where you put pieces down and connect them together. That's sort of forms of visual programming or graphical programming. And one of my small claims to fame is developing that technology back in the very, very early 80s, 1981, 82, 83. And that ended up going on to the HVAC industry, which I was in, ended up adopting that for most of the systems for programming controllers, went to graphical programming schemes about 10 years after I did that. And then I'll go on from that to model-based control. And so there'll be the 3 parts will be the graphical programming development, which doesn't have a lot of Tandy in it, just a little bit. And then the model-based control, actually I used a lot of Tandy computers in that process, so I'll get into that. And then later on after this, I'll be setting up back at the table back there. I changed my plan for the day and actually got rid of the cocoa I had, and I'll be setting up pieces of that stuff that was involved in this story. So you can actually see the real pieces, some of which still work. I spent the last couple of weeks dragging things out of the nooks and crannies, and my house is the worst mess it's ever been in because of dragging everything out of the nooks and crannies and trying to find all this stuff from 1980s. So anyway, here we go. Couple little pictures there. Dayton Microcomputer Association, it's a nonprofit for education. Our mission is to promote interest and knowledge in all facets of computer technology. We are a valuable resource for all things digital. We accomplish our mission through informative and educational programs, including its general meetings and many SIGs, which you can see this back on the table. We have a list of them. Our general membership meeting, this is in Dayton, usually is at the TJ Chumps in Huber Heights, just off of 70. Those are done as both in person and online, so you can get a Zoom link and join in from any place in the country that you can get to it with a Zoom link, probably the world. So that's the story there on the slide there for that. And our web address is dma1.org, so you can go there and see what we're doing, see what the meeting's going to be about that particular month, and find links to be able to do the Zoom thing. Special interest groups, they meet at various times during the month based on the people running those when they want to do them. And a lot of different topics, so there's some of them. Python self-study, classic computer, genealogy, single board computing, computer networking, investment, dynamic language, and the Dayton Linux users group, which is a pretty active one. It's the oldest club of its kind in Southern Ohio and one of the first computer user groups formed in the nation. In April 1976, the first meeting of the Dayton Computer Club was held at the University of Dayton. Charter members paid just $5 for a 12-month membership. That first meeting was inspired by the January 1975 issue of Popular Electronics magazine. Some of us remember when that happened. The cover of that issue featured the Altair 8800, which of course wasn't exactly what people ended up getting when they ordered one. It was slightly improved from the one that they had in the magazine. What happened on that was they ordered one, but they were out of stock on those, and they ended up getting an Altair 680, which is actually rarer now. That was based on the 6800 microprocessor, a lot smaller machine. Not so friendly as far as what could you do on the front panel. It's pretty much useless on the front panel. Everything had to be done through a monitor, but that was okay because it came with a serial port. If you had a monitor or a teletype or something to hook up to it, you were in business. So it was assembled on a kitchen table, and the club was formed, Dayton Microcomputer Association, DMA, and it's a play on the acronym for Direct Memory Access, which you might notice that. Incorporated in Ohio as a nonprofit in 1980. So anyway, go ahead. Computer Fest, we got into doing the Computer Fest, well, involved with it out of town, and then we brought it to Dayton in 1984. And that was a big program that the Dayton Microcomputer Association did for a long time, through 1984 through 2004. It grew to a really big size, 40,000 attendings per show at the Hare Arena, 120,000 square feet. So those were the big days of the Dayton Microcomputer Association. Back when you had to go to places like that to get your computer stuff, because otherwise it was online. Best Buy and CompUSA and Circuit Center City and big long list. Those things didn't exist at the beginning. Then they started showing up, and of course, eventually you have the well, at that point you already had the Radio Shack stores, and that was the advantage that Radio Shack had. They were showing up all over the place. You didn't have to go very far to get a computer. Computer Museum is a collection of classic, older computer equipment. Many came from DMA members who passed their older computers to the curator, Gary Ganger, when they upgraded to something newer. Some artifacts were donated by businesses that no longer needed them. Since 1984 Computer Fest, Gary and a team of helpers have shown a small portion of the collection at numerous events. In addition to Gary's holdings, some of his helpers add treasures to the museum display and assist with relating to history and technology. My title currently is Assistant Curator of the Computer Museum. And I'll have a little bit more on what our status at this point later. And this is an old list, which is not entirely accurate and a lot shorter than it is nowadays. We do have the 2 teletypes still. The ASR I actually repaired and have that back to working. The Selectric, I haven't got that messed with. PDP-8's a work in progress. The Altair 680, I got that back to working. Basically, it was switches and a driver IC. We have 2 Model 1s. We have a Model 4 that's an upgraded 3 and a Model 4D that's what it was. We have the microcolor computer. We have Cocos. A lot of Commodores, Atari, typical thing you'd see back in the late 70s, 80s, into early 90s. Osborne, and we got 3 or 4 K-Pros. Anyway, and all the places we've been. So with Computer Fest, you will have displays of things like that where you see the disk drives, different storage media. The one over there, if you can see where my cursor is, the cardboard stand with a little circuit board in front of it, that's one of my early, I did some artificial intelligence stuff. That's a learning machine in the 1970s, and it was all wire wrap, hardwired processor that actually learned. And then we did it at Tech Fest from 2003 through just this year. It's in February at the weekend near Science and Engineers Week, also just before President's Day. So there's some pictures of people taking in the displays there. There's our 680 again, and that's an ELF there. If you guys remember Cosmic ELFs, using an 1802 processor. We also do, Gary's doing a lot of stuff with the Raspberry Pis, so we have those set up so the students can play and get on the Raspberry Pis and use those. And this is some stuff from a couple of years ago. This is an 8800B I restored, which you can see in that video I have talking about the Computer Museum. And it's hooked up to my Y60 there, just running extended basic. And I had it at that time running the Star Trek game. You remember playing Star Trek in BASIC? I started doing that on a teletype when we weren't supposed to do it because it tied up the computer too long. The secret's out. And then I get into older stuff. Here's relay computers. This is a thing I created just in time for that show. That's a vacuum tube-based reproduction of a patent done by Joseph Desch. It's a ring counter using thyratron tubes. This is 1939, 41, in that period of time. And I'll have it set up so I can flip it and rewires it when you flip the switch, and it lets you see how C. Wynne Williams's binary counter worked. he created the first electronic binary counters using thyrotron tubes. And a guy named Hall at GE actually invented the thyrotron tubes about 1929. So that's the beginning of electronic counting and computation. And the DESH stuff, Robert Mumau stuff, played a role in invalidating the ENIAC patent because they were demonstrating ring counters used as calculators before ENIAC, and the ENIAC people saw that. So that was one of the factors, along with the Ananosov stuff, that eventually led to the invalidation of the, at that point it was a Sperry Rand, but it was the ENIAC patents. Here we are at the air show. We used to do that all the time when they did it in a place where we didn't get wet. And I've been doing Edison State for several years. And there's a relay computer at the Air Force Museum. I go up to Edison State and teach how computers work to a bunch of girls. It's the Women in STEM program. They bring in junior high and high school girls and various STEM topics. They take classes there for a day and bring in busloads and try to get more people involved in those kind of careers. Now, starting through a little list of things here, here's the next 1,000 we have in the collection. I don't have everything there, but you also notice the little book down there says Weaving the Web. That's the machine that Tim Berners-Lee used to create the World Wide Web, original client and server functions to make that happen. So we have one of those along with all the accessories which aren't in that picture, including printers, scanners, mice, software. And that's a little information on it. There's saying what I just said. That was also used to create the first app stores, and a lot of internet first were done with those machines. Of course, Doom and Quake and other Doom engine games were developed by ID Software on Next machines. Here's an assortment of 1980s computers. I'm trying to speed it up by having one picture of a whole bunch of things. So, got Ataris. There's an Apple thrown in the middle. It's a 2E actually. Some Timex Sinclairs. An Epson laptop that had the printer and the micro cassette built in, along with its handset for your telephone modem. And the one up above that is this guy here is an Aquarius, which probably most people don't know, but that one's a good one that works and everything. We have Osborne, and here's a K-Pro, and here's a bunch of Commodores. IBM PC 5150. This is actually one I had that I got from Mercy Medical Center when they were dumping it. And I have all the pieces to put it back the way it originally was, but this is what I turned it into. And it kind of shows you what you could do with an IBM 5150 if you were crazy enough. You could buy all these expansion cards, and that one has an 85 megabyte hard drive, which strangely enough came out of my Tandy 2500 SX20. And it's running in an original IBM. It has VGA graphics and a 3.5-inch floppy. The BIOS was extensible, so you could plug the car in, and it would have a little ROM in there, and they would add the functions to the drivers to make that thing work. So that's why you could take this IBM PC from 1981 or so and make it like something that would, at least several years later. And there's running DOS directory. So there's the specs on that guy, 4.77 megahertz. I did put the coprocessor in mine, so that has a coprocessor in it. I did put the, I think I have a, what was that, a V40 or something? There's a souped up 8088 in it too. My first home computer was a TI 99-4, and then I upgraded to a 4A when they became cheap. And I did a lot of stuff like Microsoft Microplan and that's Logo, if you like a little bit of AI there, expert system stuff. And I'm going to fly through that. Here's a little collection of Tandys, which is what we put on our little thing for the exhibit on the website. We have one of those, one of the electronic analog computers in the museum, plus I have mine, and that's an actual picture of mine. And then the museum has this also. In the museum we have two Model 1s, and we have a Cocos, and we have a Model 3 that was converted to a Model 4, and that's a Coco 2, and then all the pointing devices and things like I had at the table yesterday. There's my MC10 with my expansion module on it, which we'll get into, and my printer. And that's actually my Model 100 with my drive, which I need to fix. But the Model 100 works fine, and the little cups to put on so you could use the modem and stuff like that. And there's our Model 4D, and that's my 1100 FD, and that's what's left of my 2500 SX20. I passed that on to my brother's family, and I don't know where it is now. They used it for several years, and all I have is memories. So there's one of our Model 1s running just for kicks and giggles. I took a picture of that Wednesday, brought it up in BASIC just to say, hey, here, to prove it's not just a static display all the time. It does operate. The unique thing we have here is this is the expansion box. So if you remember Steve C. Arcia and Circuit Seller and the Byte magazines, and then later on he had the Circuit Seller magazine, this is the one of the projects he did. And it turned into, of course, a Micromint product, the Disk 80 expansion. So that plugs into the standard bus connector on the Model 1, and then it gives you a 32K RAM expansion, a printer interface, a disk drive controller for handles up to 4 drives, and an extension of the TRS-80 bus with a buffer on it. So that's how we do our thing. We don't have one of the other expansions. We have that one, which is maybe a little bit more unique. But so there's the specs on it. And of course, the big selling point on it was the fact that it was available at the local Radio Shack store. And basic built-in and all that good stuff. So there's our 6800, and those are actually fairly rare, so people don't pay much attention to them, but I think there's one on eBay. I don't know if we're going to get it, but they're asking for like $4,500 for it. Okay. So it's expandable up to 32K if you added the little expansion board that plugs in it that has 2 slots in it that allows you to expand it up to, with 2 16K things, up to 32 plus 1. It has 1K ROM in it, which is 4 256 bytes 1702 EEPROMs. The first one is used for the monitor program. That works. In mine, the last 3 are used for the very tiny language, which doesn't work. And it turns out the one in the middle of that stack has got some flaw in it, so I'm in the process of trying to come up with the time to fix that. It did have an 8K basic tape available if you had that much memory. Here's our PDP-8. This is a pretty good machine, 1975. It's mostly TTL, but there are some large-scale integrated circuits in there. This one's been maxed out. It's got 32K of magnetic core memory in it, in 2 boards. And that's the numbers on that guy. And that's magnetic core memory if you haven't looked at it close lately. A bunch of little donuts on wires, ferrite rings, and that's where the status of the technology was when I got into it. There's our ASR 33 after I got it working, and I forgot to put the little aluminum strip on the back when I took the picture, the little one on the front, you know, it says teletype on it. But I got it working. That's got, of course, the teletype, the BNS ASR. It's got the paper tape punch and reader, and that's all working, and I got the whole thing working. I got to fine tune a little bit, but it is functional. And if you remember in the old days, we used paper tape and punch cards. And I did punch cards with Fortran in college, and I did paper tape with HP 2000C timeshare basic. I'm spending more time on this than I wanted to. Bell Labs mainframe from 1967. I've got the parts, 100 boards from that, from Bill Eaton. And I built a little demonstrator unit that does basically counting, but with the 100 boards, I'm feeling I'm going to go crazy someday and build a working computer out of that thing, and I'll call it the Phoenix, rising from the ashes of the GE 645. Here's some analog computers. Once again, there's the Radio Shack electronic computer from 1969, which it's interesting because it's bragging about the fact that it's as accurate as a slide rule. And it always was. If you got the dials on there right and the knobs on right and there's a little pot inside you could calibrate, then it was probably as accurate as a slide rule. It does a little balancing act. Basically, you turn the pots and you turn a pot until the scale up here balances out, and then you can read your answer. And it had a little button on there that when you got it close, you push the button, and it added a little gain to that, so it got more sensitive, and it got a little finer adjustment on it that way. This is one that was used for, an analog computer was used for selling electric heat, and it did all of your basic little load calculations, you know, what kind of wall you got, and things like that, what's it made out of, what's the surface area, how big is it, what's your outside air temperature, cold going to be, so then it could calculate what your electrical consumption was going to be, and you could even dial in on these little settings down in here what the cost factor is going to be, so you could actually see what the cost is going to be for running your electric heat. This is a little bit more serious analog computer I have that is a trainer from 1967, and it's wired up. It's got 2 integrators and 3 other op amps, so it can do little second order equations and stuff. It's a neat little thing to demonstrate it. And this is one of my recorders, and you notice if you can see that, you probably can't. It's going boing, because it was running a model for the little spring and mass thing there. You pull it down and go bong. So that's the model I had running with a damper thing, and I could change how fast it dampened out to sort of like you'd have a shock absorber model. Sage Center. So we get back to, that was the Air National Defense System back in the late 50s, 60s, 70s, a little bit into the 80s before it was replaced. And I have modules from the radar data processing computer, which I now have wired up and functioning as demonstrators. And that was the logic for that. I've got modules for the 702 processor. My dad went to school on that in 1954 on the 702 for a week-long executive training class. Air Force Logistics Command. Vacuum tube-based counters you can see in the video, but I got a lot more vacuum tube stuff I've been working on. Joseph Desch and the bomb stuff, bomb schematics. That's the circuit diagram for the patent that I used to build my demonstrator with the Thyratron tubes. There's the relay computer, which I'm going to set up at the end of the day today, so you can watch that thing clicking and clacking and running a robot. That's the block diagram for it. And that's our current status of our computer museum. We have a space in a retail spot strip that we're renting as a workshop. So we really don't have it set up as a museum at this point. It's set up as a place where we're collecting stuff, cleaning it up, getting it working, producing some displays, and that kind of stuff. We may eventually, I have open houses every so often and invite people in, but most of the time it's not open. And then we may set it up at the front of it to be sort of a little bit of a better setup for a museum, but we really are looking for a bigger space to do this in. So we're still in the process of trying to grow and trying to figure out where we're going to get the funding to make that happen. So that's our needs. I just told you all that story. Artifacts are welcome. Looking for a location. And looking for places to exhibit it. So that's that one. Okay. So where am I on time? More than half, almost halfway. I didn't want to be there. Oh, I got to go faster then. Talk real fast. Don't read the captions. Okay. I think this is where I'm going. Yeah. This one's going to have to go fast to get to the last one. Okay. Basically, back in the 75, I went to work for a company called Johnson Controls. I was hired as their building automation engineer and electronic controls. At that time, electronic controls were analog. Building automation systems were based on mini computers with data gathering panels that were full of TTL logic, and they were stuck out in the motor control centers. These are HVAC systems for commercial, industrial, educational facilities, colleges. So they would be, the pneumatics and relays were used to control the air handling units themselves. So that's fans and dampers and coils and valves and all that stuff, and chillers and boilers. That was all controlled by these panels full of all these relays and pneumatic controls. But we, at that point, we're putting in mini computers to actually monitor and control those, like turn things on and off on schedules and monitor temperatures. And we actually could have a card that would actually adjust a servo-based device, so we could change pressures or change electronic value of voltages and change the set points on controllers that way. So it was the beginning of computers into that operation. So that's where I get into the stage here. Setting the stage. So there's a picture of what I'm talking about. You see this is called a motor control center. That's where your starters are. And then you have your environmental sections. So those are where you have pneumatic controls and tons of relays and time delay relays and alternating relays. So that's when we actually did relay logic with relay logic. It wasn't a PLC. So this is a diagram for an air handling unit. You can see you got these funny things. Where's my cursor at? I have a cursor. If you can see that. This is a fan. This is a fan. You got dampers in here for control of the airflow. You got valves that are controlling flow of water through coils for heating and cooling. And so that's probably heating here and cooling back here. You got pneumatic temperature sensors. So that's a typical plant diagram for an air handling unit. And this is what the control systems look like pneumatically, and that's electrically. So we have all our diagrams for all of our buckets and stuff. And then chiller plants, boiler plants. And this is actually some of the earlier stuff that was before me, but I actually worked on that too. This is a T6000 processors, which weren't a computer. They were transistor diode logic with a little bit of ICs in there. And they did the job of doing this monitoring thing over a 25 conductor cable. But I was involved with the one that was installed at Sinclair and was ready to go in 1972 when that campus opened. And anyway, and then I was involved with the initial installation of the first one at Wright State. So that was using the ModCom, which I actually have that ModCom. I rescued it from the dumpster in 1995 when they're getting rid of it. But I maintained those things all the way up until about 1997 after I'd left the company, and also since I had it as a backup computer for Cincinnati Bell. But so revolution arrives. Computers have arrived for central monitoring and control of larger facilities, but the local control at the unit equipment level was done mostly with pneumatic controls and relays. The advantage of microprocessors, digital computer technology could finally move down to the HVAC unit equipment level. At the close of the decade of the 1970s, it was the beginning of that revolution. As often is the case, the smaller players in the industry tend to introduce the innovations. Among those players was Andover Controls. They introduced their AC 256 system around 1980 and are credited with coining the term direct digital control. Anyway, they used their drum programming system. It wasn't graphical. Johnson Controls introduced its a JC8540 system in '79, and it used the TI-990 processor, which was a factor in me getting my TI-99 computer, because that microprocessor is directly related to the 990 mini computer. That's the 990 mini computer. What happened is that they did actually introduce a microprocessor at the field data gathering panel level. So they produced this FPU that used a 4084 series microprocessor, and it had a fixed program that was stored on an EEPROM. And the early ones, the EEPROM, it wasn't programmed into the 8048 itself. It had a separate EEPROM on a separate card before they finalized the software. So I get my TI-99-4, and that explains that thing. And you notice the printer there. The printer I used with that was a Tandy Printer 7. I created a I/O module so I could plug that into serial port, and then I could do more experiments with that. So I could, that ends up being my EEPROM program on a reader. I hacked the JC8540 FPU. Because that was a separate board with an EEPROM on it, guess what I did? Being curious Steve, like a lot of you people in this audience are, get into things and figure out how they work and figure out what else you can do with them. I popped that EEPROM off of there and stuck it in my EEPROM reader I created and read it off. So now I got this thing dumped out as a hexadecimal ASCII file. And so my next step on that thing was to write a disassembler. So I wrote a disassembler in BASIC on the TI that would take the hexadecimal file from the machine there and turn it back into assembler, so it would help me figure out the code. So I decoded that, figured out what was going on, and then I said, hey, I could do something different. I could have Johnson Controls now have a direct digital controller before they have one out, and, try to catch up with the market. So that's what I did. I'm working with a machine, though, that has 128 bytes of RAM and 2K of ROM. And you could theoretically expand it to 4K of ROM, but you have to do paging, so it adds a little complication to the programming. Not huge, but. So what I did is I wrote the source editor on the TI, and I wrote a compiler. I wrote a tiny basic compiler. So here's the tiny basic language I wrote. So what this allows you to do is you type in the source. It's typical basic, you see, and then I could run that through my compiler, and it would convert it to the object code in hex, ASCII hex version. And then I would download that into my programmer, and my program did the conversion from the hex ASCII into the binary and put it in the EEPROM. So that made it so I could actually program that box to do whatever I wanted to with the limitations of 128 bytes of RAM and 2K of ROM. But it worked. So I'm not going to get into details because I'm out of time, but I'm getting out of time. So if you want to see this later, you can come through and see the details on my compiler, learn how a compiler works if you haven't written one before. I wrote compilers, interpreters, P-code generators, operating systems. I go back far enough, I've done a lot of stuff. And that's a simple little program for like an interlock. Read the value of point A, assuming like it's a binary point. Read the value of point 2 if it's a binary point. A or B, then point 3 equals C. So basically, C, the relay on that end would be A or B. Just a simple example. So what happens? I send this stuff up to my context and controls research because I was doing a lot of this kind of stuff already, and I was already interacting with them. They recreated the TI 99.4 setup, but then they converted the programs over the 85, HP 85. But locally, the engineers didn't seem to think too much of it, partly because it needed more work, but mostly because they had little experience writing programs. So think about it. These guys are doing their designing by drawing things on their board, putting down symbols for pneumatic controllers and connecting them up, and drawing their little stuff for all the relay logic. But they were of the generation that had very little experience with computers. So going to direct digital controls programmed with some language is going to be a big step for them. That led me to create graphical program generation. The engineers drew the control systems on their drafting board, frequently using standard company templates for the control devices and drawing lines between them to show the interconnections. I reasoned that they could do the same thing on the computer screen, and a program could convert that drawing into a program to implement control systems. So that was the beginning of the idea there. So here's a typical one of their drawings, and you see there's boxes here with connections, and these are all pneumatic control devices, little valves. And so I had to come up with the converter program, so I created that in the TI. And these are some of the symbols I use for connectors, and some device symbols, and more device symbols. And so I wrote the converter. This shows that it works. Now these are interesting because these are actually printouts here that were printed out on the Printer 7. So the Printer 7 actually supports graphics. So you can switch it to graphic mode, and then after that, all your characters you send it are characters 128 through 255. And it just uses the lower 7 bits to set which dots this thing print says it goes across. So instead of going across and being located character by character, the head is doing column by column. But you can actually create a program, which I did, to do like a screen print graphically using that tool. It wasn't the perfect thing in the world. There's little breaks and clicks and bumps in the thing, but hey, early on stuff. There's what the graphics look like, the blue picture there. That's what the graphics look like on the TI. The below is what it looks printed out. There's my printer, and that's basically telling you what I just told you about that process. So I did the converter, and this gets into a little bit of details of how that actually works. It scans the picture, figures out what connected to what, and then each device's function is processed. It looks at the connectors it connects to and makes those connections using variables. So it assigns a variable to each one of those connectors, each one of the wires going through the system. And then this guy can say, I'm going to set this variable to something, and that's setting what's on that wire to that. And the other guy at the end of the wire can say, I'm reading that variable there, and that's getting the information off the other connection. So that's simply how it works. What happens is that, I just skipped a page, but that got reproduced up in Milwaukee in research. We did a 3-day program in '83 where we had people coming in from field engineering, advanced development, research, and some VPs, and took this all in. And basically the decision at the time was, we're going to put this out for the next product. But that's not going to be until 1990. In the meantime, 1985, Scientific American predicted that programming a computer may eventually be as simple as sketching a diagram or drawing a flowchart. 1986 Byte had a preview of National Labs LabVIEW software. It ran on an Apple Mac. Of course, that provides graphical programming configuration of instrumentation. It was introduced in 1987. Johnson Controls finally introduced their graphical programming system in 1990. You drew your pictures in GPL. It generated JC Basic, and then JC Basic was translated into object code and downloaded into control software, which that's exactly what I did with my stuff. So what happens then? About the same time, around 1990, 91, all the other bunch of people in the controls industry started using graphical programming systems. So Honeywell, Train, eventually Stafa, Invensys, whole long list of them in the 90s up into the 2000s converted over to that paradigm. So I went on using this stuff, and I went beyond the graphical programming idea of just doing control systems. I went on and got into doing plant diagrams, and that led me into the model-based control stuff. And for that stuff, I used my 1100 FD, which I brought with me today. And that was the DOS versions. And then, of course, to get it off of TI listed the TI basic programs out to the serial port. I had an IBM PC on the end of the serial port, captured that, saved it as a text file. Then all I had to do is basically go in there and correct the syntax differences between the TI basic and the IBM, Microsoft, and later on Microsoft Quick Basic programming. So it was relatively a simple thing, and then the graphics was quite a bit different. But so that got me into BASIC on IBMs. Then, of course, I get my Tandy 2500 SX, and that's when I finally load on Windows 3.0 and get Visual Basic, and now I can turn this into a Windows application, and my graphics gets quite a bit better. So there's the graphic program generator as it exists today, which I can have that running back there today. People can see how it works. It runs through 98 through 11, I think. I know it runs through 10. I haven't tested it on 11. There's no reason why it wouldn't run on 11. And that I sell on my website, pretty cheap price. But it's a general purpose graphical program generator. You can create your own symbols. You can create your own things that it generates. It have an attribute file system that goes back that I started in the DOS version, but it's improved into the Windows version. That the attribute files are associated with the symbols, and when it processes a symbol, it tells it what to do. So it can generate whatever you set it up to do with that attribute file. You could generate Python from a diagram. You could generate web pages from a diagram. I've done that. You can do assembly language from you can do hex ASCII from whatever you want to. You can generate from a diagram. So you could program your Tandy computers in assembly language using pictures of the processes, or whatever you were wanting to do with it, but which is what I actually did. So there's a diagram, blum, blum, blum. Okay, I'm probably out of time, but I want to do a quickie run through of what I'm going to show you today back at the table. Am I back far enough? Yeah, I'm back far enough. Okay, here's the model-based control stuff. This gets really interesting. It's actually beyond where we are today. So anyway, I used the TI-99/4A to develop graphical programming ideas. I got to use it to create intelligent diagnostic systems and programming from a plant diagram instead of a control diagram. So here's the machine I had set up yesterday, and it's going to be set up again today. That was my low-cost lab system from 1984. I designed and built this I/O module that I used with the MC10 to take measurements and control experiments. And these experiments contributed to the development of model-based control. And you can see my GCP 115 was a great tool in that because I could plot out my results. I/O module provides 8 0 to 5 volt analog inputs and 4 relay outputs. It attaches to the main bus edge card connector on the MC10. Address decoding circuit places it at address 2480 decimal. Peaks and pokes are used to communicate it within basic. So here's just explaining how that works. And then there's the program I'm running for just the thermostat demo back there, where it just it's reading the temperature and turning a relay on and off. The temperature is a thermistor and a tube with a light bulb in it. So when it's cold, it says I'm cold and turns on the light bulb, warms it up until it gets up to the set point. When it gets up to the set point, it turns off the light bulb, and then it cools off back down to the other side of the differential on the control and turns it back on. Not the fanciest thing, but it just proves the fact you could do that, right? And I did fancier things than that, which I'll get into. So there you go. So some of the graphics I did a lot of surface plotting related to modeling of systems. So these are related to mixed air damper processes, how the mixed air mixes with outside air, return air, and the mixed air and return and the damper position, and what effects these all have. And I could see what the process gains are and everything else. This was experiments I did with it to investigating using pneumatic actuators. We were still using those, and some of the research I did and projects I did actually ran into a little bit of resistance and support from Milwaukee, because they were saying we're phasing out pneumatic actuators. And you know what? I still go on sites today that still have pneumatic actuators on them. So anyway, this was to introduce electronic control. So I eventually produced a thing called an electronic pilot positioner, and a few other things that got even more fancy than that. But these plots are showing what happens. This gray thing down here is a pneumatic actuator at the time. So what it is, it's got a spring inside, it's got a rubber diaphragm and a piston in here. And you put air into the end of it, and as the pressure builds up, it eventually gets up to a high enough pressure that it starts to compress the spring. So that's when the stroke starts. And then when it gets to the end of the travel, it stops. So what this is demonstrating is using that experimental setup of mine, I could tell it turn on the airflow, and then I could start sampling what the pressure is, because I had a transducer to give me a pressure reading, convert it to voltage to go to my A to D converters. So this is a plot showing the pressures, and the interesting thing it demonstrates, you see these little elbows here when it comes up first. Can you see my cursor? Yeah. It comes up at a fairly straight line, and it's a fairly steep line, because at that point it's a small volume. And then when it gets to that break point, that's when it actually starts to stroke. And so now you see this long line going up here. Okay, where did my cursor go? Here. And then here's where it gets to the point where it stops moving again. And you can see the definite break in the characteristics there that lets you know. And then it goes up at a less steep angle, because now it's a bigger volume. So you can not only see what the volume of the actuator at that point is, but you can see the stroke, the endpoints of that. So you can read off of that the thing operates from just under 8 psi to probably 12 psi or so. That's the stroke on. So without actually knowing it, you can actually see that from that pressure characteristic. So I took that a lot farther than that, but that's an example of the stuff I did. The Tandy Model 100, I used that a lot in developing some stuff. The main thing I used it for was a terminal. So I used it as a terminal with a lot of my processors I built, which were all, I'll have one of them back here. I have my Z80 machine back there. I did a Z80 machine that did multitasking, I did a multitasking, multi-user operating system on a Z80 and included a BCD, variable precision scientific math package that did what you'd expect. It did logarithms, powers, trig functions. So it's kind of a fancy math package on a Z80. Well, not really. But I did that on that. And what I used this thing, you could go in there and write text files. So if everything I'm doing is going through the monitor program I have in the Z80 machine already, I just write these in hexadecimal ASCII files. And I can just save those as a text file on the Model 100. I could also save them as text files on my floppy drive you see there. So that's where they're residing right now. I got a bunch of them on the floppy drive, and I got to fix my floppy drive so I can see those files again. But anyway, or I can just upload them from the box itself. And then you can also download it by just going into Telecom, and they had a download function. You hit download, and I go into Telecom, and I give it my monitor program command for reading or writing, and then I go into using the Telecom. I hit the download button. Say if I wanted to read what was in the box, I do upload to put it in the box, and I do that, and then it would just I was telling it how much I wanted in the command, and it would just dump it out, and it would show up on the screen as and it would be dumping it into the text file I specified when I clicked the download button. So now I could upload and download stuff using the Model 100. So it was really handy for that. So I developed a lot of stuff with that. This is that machine I was talking about. Some of my machines I did at various times. There's a fourth machine there that was multiprocessor. I have this ends up being the Z80 machine. I used the Y60 terminal for most. I did actual graphics on this. I did the graphical plant diagram stuff on this too, using the Z80 machine, and using the Y60 actually allowed you to find a certain number of characters on bit patterns. So I had little graphic characters. On the multitasking, multi-user stuff, I was doing windows. The Y60 has a little framing characters you can use to frame windows. So I could have multiple tasks running at the same time, and I could have those in different windows, like windows before windows. A little bit before windows, not a huge amount. And then, of course, there were other people doing windows before windows. So that's the machine I did all that stuff on. Just told you that. And then the next step is my 1100 FD gets involved. So I'm running MS-DOS on that. And this is an experimental setup, a picture from the time. That's my 1100 FD. That's my Star Micronics Rainbow printer back there, which I was using at that point. And then this funny looking thing made out of PVC pipe is actually my little test model. So I'm playing around with trying out model-based control systems. And instead of doing it on a full-size unit, I've got this thing made out of PVC pipe. And I can take it apart, put it together in different ways, model, make a system representing different systems, different type of systems, using that scheme. So that was my test bed. And then I have there's the test bed. I dragged this out from wherever it was, dusted it off, and there it is. So there's the little interface board. So it talks to the serial port to the Tandy, and it had a microchip. I did a lot of microchip stuff in my work. I did a lot of embedded controllers. 16C84 for its processor, which is an early one, and then various I/O ICs, ADC converter, which I believe that's an 8-input one. And then I had a DAC for my analog outputs, which I really didn't use those very often, but I used it on that. And then, of course, the typical Max 232 for my RS-230. Then signal conditioning, I had two quad op amps and a regulator IC. And then I built this little power supply and a regulator that allows me to vary the speed of the motor. And there's a differential pressure sensor there in the foreground, which is reading the pressure across the unit. So it's telling me what my discharge static pressure is, just like you would on a real unit. I had dampers controlled by rail control servos, so I could change the positions of the dampers. So that was my test platform that I could have on my table. I didn't have to go out to a work site and actually mess with a real air handler in it. And that was an electric heater with a little triac circuit that pulse modulated it. This is what the diagrams look like in the DOS world. They're not that fancy yet, but I could actually model things. In this case, it was pumps and valves and stuff for water. In this case, it's the air handling unit, and it's just a straight shot one. And I tried running that program to get this picture, and it came back with a fault, and I'm thinking it's because it wasn't hooked up to the actual system to talk to. So anyway, I could draw these things up. When I plopped down these symbols, when I processed it in the graphic programming generator, it would actually process that and create a model. It would model the sensors, it would model the fans, model the coils, So it produces an actual model. And in this case, the model is running in BASIC. It's running in QBasic eventually on the Tandy, and talking through the serial board at the same time, communicating with the real system. Well, the idea of model-based control is that you can you produce a model. Normally you think about control systems being like PID loops or control loops. This temperature sensor here is going to feed back to a controller here that works this valve here, that works the water flow through this hot water coil, and based on your setting, it's going to work that valve and keep the temperature here what you want. That's your typical single loop type stuff. When you get into model-based control, instead, you don't have that anymore. You have all these sensors that are introducing information into the model, and the model is solving for everything. Everything is an input and an output. So the power of this thing really comes when you get to the idea of that's what's going on there. Because everything is modeling everything else, the way you tell it what you want to do, you give the systems goals. So you go into a particular part of the system and you force the model to what you want. And when you force the model to what you want at that point, the model solves for what it has to do with everything in the system to accomplish that. That gives it the power to do what happens if something fails. If something fails in conventional programming, you would have to write every piece of code saying, well, if this fails, what am I going to do? In model-based control, that doesn't happen, because what happens is when something fails, it's going to use everything else it has in the system to figure out how to keep the system operating with that failure in place. So it's a very, very robust system. Also what happens in that is an example of one of the demonstrations I did at one time, which was, I did a lot of demonstrations. I could walk up and pull off a temperature sensor or a pressure sensor while this thing is running. And guess what? It kept right on running. It reported the fact that it was saying, this is this, but I think the real pressure or temperature is this, because it's using everything else in the model to say, well, based on everything else, that can't be that, it's got to be this. So because it knows that, it will automatically keep operating even though that sensor's not working anymore. So just think about how powerful that is. This applies to not just HVAC stuff, it's like airplanes. Say remember the flight that was in the Atlantic and that they had the pitot tubes get iced over and they lost all 3 of their redundant airflow sensors, so they lost their airspeed? Well, you could use other systems in the airplane to tell you what the speed of the airplane is. And from that, you can model what it is, and you know what the reading should have been, even though you lost the reading. So it makes very reliable systems. It has a very much of an artificial intelligence flavor to it. It's really involved in exactly how parts of the brain actually work this way. In my models, they're individual pieces of models, and they're talking all the time back and forth between each other. It's a distributed model, even though it may be running on the Tandy computer or some other computer as a process that's doing the whole thing. It can be done as a distributed process too, where these guys are all talking back and forth with each other. Well, that's how it's distributed and how the information gets sent around. It's related to neural nets, but more powerful than neural nets. It can learn the systems, but it can learn faster than neural networks can. And getting back to the idea of how it relates to the brain, well, I did a lot of research into how brains operate back when I was doing this stuff. And you have neural clusters. If you have a big neural network and you try to do too much with it, it becomes unstable and it takes forever to train it because of the fact it's too big. The brain solved that problem because it has little clusters. So you have a cluster of neurons involved with this and a cluster of neurons involved with that. So it's like these individual neural networks, but they're talking back and forth between each other all the time. Same thing as my model-based control does. So I often read an awful lot. You know, science news puts me to sleep every night, but it didn't work last night. But anyway, so I get involved in all kinds of things along those lines. And so I can read other people's research, and I don't have to do it because I can read their research and see what they didn't know what I was looking for, but I can take their data and figure out, oh, this fits my model or my idea. So an example of that is that there was research done. Of course, I did a lot of research in visual systems. I've developed artificial vision systems, things I could use on autonomous vehicles and robots and stuff so they can actually see and understand the world. And so the brain, you have your visual cortex back here. And in your visual cortex, there's edge detectors. So we can actually see the edges of things. And there's also end stops and corners. So there's actually neural configurations in there that are able to detect those features in what you're looking at. Well, up here you have your somatosensory cortex up here. That's where your touch sensors are. Okay? So this is what you're going to feel edges with. And back here is what you're going to see edges with. So guess what happens? When you touch something, it's actually activating neurons in your visual cortex for the edge detectors. When you see something, it's actually activating the sensors in your sensory strip for the edge detectors. You know, one of the big things you learn when you're a little kid is that you learn your eye-hand coordination. So this is how this all ties together. You can feel something and feel the shape of it, and you can visualize that. So that example from the brain is an example that shows exactly how the model-based control paradigm also fits a large portion of how the brain actually functions too. So I think I probably, there's model-based control with the current graphic programmer generator. I use it for graphics on my control systems for my customers, because you can just plop down symbols and make a graphic, but you can also have that graphic actually be functional of some sort. And that's it. So, any questions, answers, or we can talk about it later if we need to, because I'll be setting up some of these pieces back there at the table, the Dayton Microcomputer Association table back there. Oh.
Was happy to hear about the 8048. That's a nice chip.
Huh?
Was happy to see the 8048 used in there. That's a nice chip.
Oh yeah. Yeah, I used them because they were, it turned out they were used for a lot of these data gathering panels. Honeywell used them too. And I have one of my little boards I showed there actually was a board for just an 8048 that was, I was using it like I would have used a PIC processor later on, just for a little embedded controller type stuff. So yeah, it was, its limitation was it was limitation. You didn't have that much RAM. You could get a little bit more RAM in it, and depending on which model number it was, and you could get the EEPROM inside it, like I said, up to 4K. So I was cramming it pretty good, doing a tiny basic, plus the actual point handling routines and all that inside inside that machine's capabilities.
Yes, little brother shows up in Model 2 keyboards, and Excel shows up, I think, in the Model 12 and 16 keyboards.
Yeah. I also did a machine that I glanced over it, but I did a fourth interpreter in it and a monitor that looks more like fourth than anything else. So you got words, and you can add words to it, like fourth. And that I used a 8070. The 8070 was kind of unique because it supports multiprocessing. So that was my multiprocessing machine in the 80s. You could actually plug in up to practically up to 4 processors. Because if you went past 4 processors, the processors are just waiting all day for the next guy to give it its turn. But they had to build in architecture for doing the handshaking to let this guy take his turn, this guy take his turn, and but they were using the same bus. So if you're doing something inside the register, you might get away with it. But as soon as you had to go out to the bus for memory, you had to wait until your turn to actually get on the bus. So that was the limiting factor on that multiprocessing system. That really, if you went past 4, there wasn't a lot of point in it. And that same machine could use what was called an 8052. Is that the right number? The 8052 had the built-in tiny basic in it. So there was a lot of interesting chips that were popping up in that time. So anyway, any more questions? I put you to sleep.
So these model-based controller systems and so forth, I would imagine that they've been adapted for anything that's critical. Maybe think of things like nuclear power plants, rocket engines, anything where if there's a failure, you want it to try to be as tolerant and responsive as possible.
Absolutely. There was another part to that I didn't get into, but that was another part of the plant diagram stuff, which could be other things. Since I had written programs that could follow a diagram, I could follow a plant diagram. So that introduced the ability to have a artificial intelligence level on top of this. So the model-based control is sort of like what you do automatically without thinking about it. This other layer is what you do when you think about it. So you could actually have this thing look through the model and figure out what's going on. So when something fails, it could actually consciously go back and say, oh, well, if this has got this problem, then it has to be upstream of that. And maybe it's the fact that the chiller water pump's not working. So it can actually give you a description of the problem and make an analysis of that simply by using the diagrams. So that's not as fancy as the model-based stuff is, but it adds that level up there, which is now an interactive, intelligent agent that you can interact with. And it has an understanding of what's going on because it has connections to the model and knows how everything's connected. So that's the power of the plant diagram. And those plant diagrams go beyond, like we're saying, the plants you're talking about, but it goes to airplanes, it goes to rockets, it goes to any kind of a system you can really think of that does something actively. Is there any more secrets I can tell you guys today?
You can tell us, but then you have to go.
Yeah. Shoot you with a memory dissolver. Any more questions? Well, like I say, I'll have it set up back there, and you guys can come by and see some of this operating. And I probably have my graphic program generator running on my second laptop back there. I'm going to have the Z80 machine hopefully running, hooked up to my Model 100. Not that I'll be doing anything other than the fact I can show you I can download programs from the Z80. And I'll have my MC10 demo running like I had running yesterday. So you're welcome to come back and see that after I get it set up. It's going to take me about a half hour or so to get that going. Okay.